antiderivatives and the indefinite integral. Antiderivatives. If the derivative of capital F of x is lowercase f of x, then we call capital F of x an antiderivative of little f of x. So what does that mean? That means if we start with the derivative of a function and we go back and we find the original function, that's called the antiderivative. For example, if little f of x equals 2x, then an antiderivative is going to be what? Well, we're trying to answer the question, what has a derivative of 2x? So if we think through the functions we've looked through, we might say that an antiderivative is x squared, because if you take the derivative of x squared, you get 2x. However, you could also have said that f of x is x squared plus 1, because if you were to take the derivative of that, you would get 2x. Because the 1 is a constant, it would go to 0. Similarly, you could have said x squared minus 3. Because again, if you take the derivative of x squared minus 3, you get 2x. So it turns out that when we talk about antiderivatives, there's not just one antiderivative, there's actually a family of antiderivatives. So when we find the antiderivative of a function, what we normally do in order to talk about all these different antiderivatives we could have is we notate it x squared plus c. So that means that we're recognizing that the function itself has to be x squared, but we could add or subtract any constant we wanted and it would still satisfy our definition of antiderivative. Now, later on in this section, we'll learn about times that we can solve for c. So then we'll get a specific antiderivative. But for now, we're going to be looking for the general antiderivative. So how do we know when we want to find the antiderivative of a function? Well, first and foremost, it might say, find an antiderivative of this function. That'll be very clear. However, there's another way we can ask and use notation, and that's called the indefinite integral. So you may recognize the symbols a little bit here because we use the integral symbol when we were talking about area under the curve. However, what you'll notice here is that there's no numbers on the bounds. So when we use the integral symbol with no numbers, then we're looking for what's called the indefinite integral, which means that we're being asked to find the antiderivative. So when you see the integral symbol of a function with no numbers on the bounds, that also means that we're looking for the antiderivative. So you'll either see this notation with the integral or the question will use the words antiderivative. Now, I want you to notice a couple things here. Oftentimes when we're talking about the antiderivative, we use little f of x to talk about the derivative and capital F of x to talk about the antiderivative. That's the convention in a lot of math courses, so you'll see that used a lot here. It doesn't have to be that way. We can use the derivative notation with the hash mark, but generally, when you use the lowercase and the uppercase, it's assumed that we recognize that the lowercase represents the derivative and the uppercase represents the antiderivative. So again, when we're asked to find the antiderivative of little f of x, we're trying to answer the question, what has a derivative of little f of x? So there comes about a very important difference when we use the integral symbol. When you use the integral symbol with no numbers on the bounds, that's an indefinite integral. And again, that means that you are looking for the antiderivative of the function. So your answer is a function. When you have numbers on the bounds, that was called the definite integral. And when you have the definite integral, you are computing the area under a curve between 2 points. So you're expecting a numerical answer. So even though the symbols look the same, they're computing different things. So make sure you're careful and you read the questions carefully to determine if you're looking for an indefinite integral or a definite integral. Okay, so now let's practice some of the methods we can use to find indefinite integrals to use to find antiderivatives. Example 1. Which of the following functions is an antiderivative of f of x equals 32x to the third? Now, in this example, we are given some choices. So we have some answers and we want to test whether or not they could be an antiderivative. The nice thing is, if you have some possibilities, we can take the derivative of the function to see if it gives us little f of x, because that's the definition. So for a, if we were to take the derivative of this function, we're going to get 48x. Well, that's not little f of x, so this is not an antiderivative of that function. For b, if we take the derivative here, we're going to get 32x cubed. Well, that's what we were looking for here. So that means that b is an antiderivative. And then finally for c, if we take the derivative of that function, we get 32x to the 7th. So the power is wrong. So that is not an antiderivative. So if you have a function that you think might be the antiderivative of the function you're looking for, you can always take the derivative of it to check against the original function. But most of the time, we're not going to have options. Instead, we're going to be trying to figure out what the antiderivative is. So remember, back when we first started learning about derivatives, we had a whole chart that helped us remember the different methods and processes we could use to take basic derivatives. Our table looked like this. So basically what we need to do is we need to reverse our table, because instead of going from the function to the derivative, we're now going from the derivative back to the original function. So some of that translates really well. So for example, if we start with 0, we end up with a constant, right? That's our plus c that we get for everything. If we start with a constant, it becomes our constant times the variable. So those ones translate nicely. However, when we get to the power rule, things become a little more tricky. So it says if you have px to the p minus 1, that would go back to x to the p. But we don't always have the right constant in front. So let's look at a case of this and see if we can figure out how we can rewrite this formula to make a little more sense. So let's start with the function x cubed. We know that if we take the derivative, we're going to get 3x squared. So now we want to start with our 3x squared and think about what we're going to need to do to get back to x cubed. So here, we know that we're going to have to increase the power by 1 to go back to the original function. So we're going to have 3x to the 2 plus 1. So that gets us the right power. However, if we just left it like that, we'd have an extra 3 in front. So we actually have to remember to divide out that 3, right? So if we add 1 to the power and we divide by 3, that's what will get us back to x cubed. So what does that actually mean we're doing, right? So we're adding 1 to the power, but then notice that the new power is 3, and we're dividing by 3. That's not a coincidence. Turns out that if we want to take the antiderivative of x to the p, right, some power of p, that we are going to add 1 to the power, just like we did before, and divide by the new power, just like we did over here. We divided by this new power of 3. So that's how we undo the derivative. Because when we did the derivative, we multiplied in front and subtracted in the power. So to undo multiplication in front and subtraction, we would need to do division in front and addition in the power. So that'll undo it. So in terms of sines and cosines, the antiderivative of cosine is sine. The antiderivative of sine is negative cosine, right? So that negative will transfer. And then the others we'll look at on our new chart. So I took the derivative row or the derivative column and moved it to the left. And now we get a whole set of new formulas here. So again, let's look at each one. If we start with nothing and you take the antiderivative, you get plus c. Because we know if you take the derivative of c, you get back to 0. So that means all of our antiderivatives have a plus c on the end. If you start with a constant and you take the antiderivative, it picks up the variable of integration. So what that means is if your function is defined in terms of x, it picks up an x. If it's defined in terms of t, it picks up a t, so on and so forth. We said x to the p becomes x to the p plus 1 divided by p plus 1. So you're going to add 1 to the power, divide by the new power. The antiderivative of cosine is sine. The antiderivative of sine is negative cosine. With exponentials, remember we multiplied in front by a constant. So now to undo that, we have to divide by that constant. So if you have a to the x, the antiderivative is a to the x divided by the natural log of a. The derivative of e to the x was e to the x, so the antiderivative of e to the x is e to the x. We always love that one. Now let's talk about 1 over x. So we know that the derivative of the natural log of x is 1 over x. But now we're saying that the antiderivative of 1 over x is the natural log of the absolute value of x. Why do we have to put in that absolute value? I want you to think about the domain of 1 over x. The domain of 1 over x is all real numbers except for 0. So that means when we find the antiderivative and we map that domain, we have to be careful because before we were allowed to plug in negative numbers. But natural log is not defined for negative numbers. So in order to keep that domain consistent, we have to implement the absolute value so that the domain remains the same. So we end up with the natural log of the absolute value of x. Now, there's 2 more special rules we can use that are actually rules that we pull from the chain rule from derivatives. So I want you to remember that if you were to take the derivative of e to the cx, you would do a chain rule and you would end up with c e to the cx. So you end up multiplying by the constant in front. We're now going to take a step and just make it a formula since this comes up a lot. So if you take the antiderivative of e to the constant times x, then it's going to be e to the cx divided by c. We have to divide that constant. The same thing's going to happen with sine or cosine. If you have sine of a constant times x or cosine of a constant times x, you take the antiderivative, but then you divide by that constant. So that's a rule we can use now without having to do the opposite of the chain rule, which we'll learn a little bit later, and it'll make our lives a little bit easier. So these make up the basic antiderivatives. These are the ones that you're going to want to learn really well. And basic, it doesn't mean easy. It means foundational. It means that the things that we're going to do in later chapters are going to boil back down to these rules. So you're going to want to work on memorizing them and getting really comfortable with them so that you can remember them quickly and efficiently when things start to get harder. But for now, we want to practice these rules and make sure that they make sense. So let's take a look at some examples. Example 2. So here we have 5 indefinite integrals, which means that we're looking for the antiderivative of 5 different functions. So we're going to look at each one and make sure we understand how to use some of the rules that we've looked at to get the solutions here. So we're going to start with the first one. Here we have a constant. We have 10 dx. A constant is going to pick up the variable of integration. So I know that my variable here is x because of the dx. That's how I know what variable to assign to any constant I have. And I know that if I take the derivative of 10x plus c, I'll just get back 10. So that matches with what I know about antiderivatives. Similarly, I have 15 dt. So here, my 15, again, is going to pick up the variable of integration, only now that variable is t. So I end up with 15t plus c. Now, the other questions here are going to require my power rule. So I need to remember that one. And that's the one that we'll probably use most frequently. So remember, I'm going to add 1 to the power and then divide by the new power. So for x cubed, I'm going to get x to the 4th divided by 4. So I added 1 to the power and then I divided by the new power. I have to add first to get the new power and then divide by that number. For t to the 2/3, I'm going to have to add 1, and I'm going to be really careful because I have a fraction here. So I end up with t to the 5/3 divided by 5/3. We don't like to have fractions in the denominator of a function, and if you divide by a fraction, it's the same thing as multiplying by the reciprocal. So I'm going to rewrite this. Instead of dividing by 5/3, that's the same thing as multiplying by 3/5. So 3/5 t to the 5/3 plus c. Be really, really careful when you have functions that have fractions in the power. Last but not least, we have x to the 5th. We're going to add 1 to the power, which becomes x to the 6th, and divide by the new power. So we have x to the 6th over 6 plus c. So again, we're trying to get comfortable with some of the ideas of how these antiderivatives work, and we're going to bring in some more rules, just like we had for derivatives, and see how they match up. So the next one is our constant multiple rule. So let's remember that from before. So remember with derivatives, if you had a constant and then you took the derivative of a function, that constant multiplied the derivative. The same thing happens with antiderivatives. If you have a constant, m, times a function, you can actually pull that constant out front and take the antiderivative, and you end up with m times the antiderivative. So that constant carries through if it's multiplied in front of a function. So that constant multiple rule, it carries over. All the constants are coming with us. So let's see how this looks when we try some practice problems. Example 3. So we're going to look at some more of these antiderivatives, and we're going to use our constant multiple rule to make sure we understand how these constants impact our final answer. So the first one, we have 3 over x dx. So I can rewrite this as 3 times the integral of 1 over x dx. So now the antiderivative of 1 over x is the natural log of the absolute value of x plus c. So the 3 ends up in front. It doesn't end up in the argument of the natural log. It ends up multiplying the natural log in front because of our constant multiple rule. Now, you don't have to pull the constant out front. As long as you remember it's going to multiply your answer, it's fine to leave it with the function. So let's look at the next one to see what that looks like. So here we have 12e to the negative 6t. So I know from my constant multiple rule that the 12 is going to carry along. And I know from my formula list that I'm going to get the same thing back divided by the number that's in the power. So here, I get the same thing back divided by negative 6. If I want to simplify this, I have 12 divided by negative 6. That's going to give me negative 2e to the negative 6t plus c. So that constant multiplied our antiderivative, but then we were able to simplify it a little bit because of the number that came out of the power. The next one, we have 4t to the 1/3. So again, we're using our power rule. We're going to add 1 to the power and divide by the new power. So here we have 4t to the 4/3 divided by 4/3. But we don't want to divide by a fraction here. So instead, we're going to multiply by the reciprocal. So we have 3/4 times 4t to the 4/3. The 4's are going to cancel here. And I'm finally going to be left with 3t to the 4/3 plus c. So again, when I simplified here, I didn't want to divide by a fraction, so I multiplied by the reciprocal, which was 3/4. And when the 3/4 multiplied the 4, I ended up with just a 3. The next one, we have 12x cubed. So here again, I'm going to add 1 to the power, 12x to the 4th, divide by the new power. I can simplify the 12 and the 4, so I get 3x to the 4th plus c. In general, we're going to want to combine our constants to be in the simplest form. So here again, we have 3x to the 4th plus c. The next two questions involve sine and cosine. So we just have to be a little bit careful about when the negative comes about. So with sine, right, the antiderivative of sine is negative cosine. So that means when I take the antiderivative, I have 5 times negative cosine of 2x. And now because I have a constant in there, I need to divide by that constant. So I'm going to simplify this a little bit. I'm going to pull the negative to the front, and I'm going to write this as negative 5/2 cosine of 2x plus c. So the negative and the 5 and the over 2 all got pulled to the front just to make things a little bit easier. For the last one, I have negative 4 cosine of 2t dt. The antiderivative of cosine is sine. So that means I'm going to have negative 4 times sine of 2t divided by 2. Now again, I want to simplify. Negative 4 divided by 2 gives me negative 2 sine of 2t plus c. So what you might be noticing is that we have to be a little bit careful with our algebra when we do these antiderivatives. But other than that, it's mostly memorizing the formulas and getting used to the patterns, just like it was with derivatives. Now, just like before when we did derivatives, we do have to be careful when the algebra gets tricky. So for the next example, we're going to look at a couple of examples where we have to do some rewriting before we can find the antiderivative. Example 4. Use the formulas to find each of the antiderivatives of the following functions. So for each of these, we're going to have to rewrite it before we can find the antiderivative. So the square root of x is going to become x to the 1/2. So the antiderivative of x to the 1/2 means we're going to add 1 to the power, so that becomes x to the 3/2, divided by the new power. So if we divide by 3/2, that's the same thing as multiplying by 2/3. So we get 2/3 x to the 3/2. And we can leave our answer like this. For the next one, again, we need to do some rewriting. We can't take the antiderivative with the function in the denominator, so we need to bring it up. We have 4x to the negative 3. So if we want to take the antiderivative of that, we're going to add 1 to the power. So we have 4x to the negative 2. So remember, negative 3 plus 1 is negative 2, divided by negative 2. And we're going to simplify this a little bit. So 4 over negative 2 is negative 2. And in general, we don't want to have negative powers. So I'm going to rewrite this as 1 over x squared. I'm going to put it back in the denominator. And then I'm going to take it one step further, and I'm going to put that negative 2 in the numerator. So I have negative 2 over x squared. That's going to be the most efficient way to write this and the easiest way to visually see the answer. So again, it required some algebra to get to the final answer, but hopefully that's not too bad. So finally, for part C, we want to do some rewriting. So we have x squared to the 1/5. If you have a power raised to a power, you can multiply your powers together. So we have x to the 2/5. So our antiderivative here, we're going to add 1 to the power. So we get x to the 7/5. And then we would divide by 7/5. But we don't want to divide by the fraction, so instead we multiply by the reciprocal because they're equivalent. So we get 5/7 x to the 7/5 plus c. We would have had a plus c up here too. Everything gets a plus c. So again, if you have something that's algebraically not ideal to follow our rules, you have to take the first step to rewrite it into the right form in order to be able to apply the formula. In order to do with roots, you have to turn them into numbers. And again, you can't take the antiderivative of something in the denominator. So if you have something in the denominator, you need to first bring it up so that you can work with it. The next rule that we have that we looked at before with derivatives, and now we'll apply to antiderivatives, is that if you're taking the antiderivative of two functions that are separated by either addition or subtraction, you can go term by term, taking the antiderivative, and then put those results together. So again, as long as you're separated by addition or subtraction, you can go term by term to find the antiderivative of each piece. So let's take a look at a couple of those. Example 4. Use the formulas to find each of the antiderivative of the following functions. So for the first one, again, we're going to go term by term, and we're going to find the antiderivative of each piece. So we start with x to the 5th. That becomes x to the 6th over 6 minus, then we have 2x cubed, because we add 1 to the power, divided by 3, plus, and then we have 6x squared divided by 2, so we added 1 to the power, divided by 2, plus 1x plus c. So remember, the 1 is going to pick up the variable, which was x. And so here, the only simplification I would do is that 6 divided by 2 could be written as 3x squared. Again, you don't have to write the 1. If you don't want to, you can just write it as x, and the 1 would be implied. That's up to you. For part B, again, we're going to go term by term, and we're going to test out each of our rules here. So the first one's exponential. For an exponential function, you get the same thing back, but then we divide by the natural log of the base. Remember, with derivatives, we were multiplying by the natural log of the base. Both antiderivatives, we have to undo that, so we divide. For the next one, we have 2 over x. So that's the same thing as 2 times 1 over x. And we know that the antiderivative of 1 over x is the natural log of the absolute value. So we have minus 2 natural log of the absolute value of x plus. Then we have another exponential function. So with exponentials, the constant of 2 is going to multiply the antiderivative of 3 to the x, which is 3 to the x, divided by the natural log of 3. So again, that 2 has to carry, and algebraically, that 2 cannot be combined with the base of 3, because that base of 3 is part of the function. So don't multiply that 2 and 3 to make 6. That's not how that works. The 2 just multiplies in front the way it is here. And then finally, the last term is sine. So the antiderivative of positive sine is negative cosine. So we end up with minus cosine x. So again, we were able to go term by term and find the antiderivative of each piece. Part C, we're going to have to do a little rewriting before we find the antiderivative. So the first term stays the same. The second term becomes x to the 1/4. And then the last term, we get 2x to the negative 3. So again, I had to turn my symbols into numbers, and I had to bring anything up from the denominator so that I could use my power rule. So my first term is going to become 10x to the 5th divided by 5. So again, add 1 to the power, divide by the new power, minus, same thing for the second part. We're going to add 1 to the power. So we're going to end up with x to the 5/4 divided by 5/4. But if you divide by 5/4, that's the same thing as multiplying by 4/5. That's the reciprocal. Plus, now here we have 2x, and if we add 1 to the power, that becomes negative 2 divided by negative 2. So here, if we were going to do any simplification, we got plus c. Don't forget our plus c's. They're easy to forget. The only simplifications we would do 10 divided by 5, and we'd turn that into a 2. And we would take 2 divided by negative 2 and turn that into a negative 1. And if we wanted to, in that last term, we could put it over x to the positive 2. So if we rewrite this one with our simplifications, we have 2x to the 5th minus 4/5 x to the 5/4 minus 1 over x squared plus c. So again, that's the typical way that we would rewrite this in order for it to look most visually cohesive. And that's the antiderivative of part C. If we want to take the antiderivative for part D, again, we're going to go term by term. So the first term is exponential, so we use that rule. That rule says we get the same thing back, divided by the natural log of the base. The antiderivative of e to the x is e to the x. Then we have the power rule coming up. So here we had x to the 2/3. If we add 1, we get x to the 5/3 divided by 5/3. But if you divide by 5/3, it's the same thing as multiplying by 3/5. Minus the natural log of the absolute value of x plus 6x plus c. So again, we're just really getting used to these rules and these formulas, and the better we can get at these before we try the more complicated processes, the better it will go overall. So let's try one more example that just gives us a generic C, but also has some algebraic letters in it, which sometimes can be a little confusing. Example 5. Use the formulas to find each of the antiderivatives of the following functions. So we have f of x equals x to the a minus b e to the cx plus sine of dx plus e over x. So here, a, b, c, d, and e are going to be constants because it's f of x, which means that x is your independent variable. So we want to use the same formulas that we've been looking at, but we have to figure out how to apply them when we have a constant that's a letter that's representing a placeholder for our numbers. So as long as we're really careful about this, we should be able to find the antiderivative. So for part A, we start with x to the a. So we're going to use our power rule here. So we're going to add 1 to the power and divide by the new power. So we end up with x to the a plus 1 divided by a plus 1. Then minus, we have b e to the cx. So we know with exponentials we get the same thing back, and the b has to multiply it because of the constant multiple rule. But one of our special formulas said that if you have a constant up in the power, that we have to divide by that constant. So again, that came out as a result of the chain rule, but we're expediting it with a formula here. So whenever you have a constant up in the power of e, you are dividing by that constant. So we end up with something that looks like that. Now the next term, we have sine of dx. So again, we notice that there's a constant inside the argument. So the antiderivative of sine is negative cosine. So we have minus cosine of dx. But then our special rule says that we have to divide by whatever the constant is. So divided by d. Finally, we have e over x. So the antiderivative here, the e would come out front, and we'd have the natural log of the absolute value of x, and then plus capital C to represent the constant to make it a family of antiderivatives, not to be confused with the c in the e term. You could use a different letter for the constant at the end if that makes it a little bit easier for you. You can call it q or j or triangle or whatever you want to call it, but it would represent a placeholder for that constant. Part B is similar. We're again trying to find the antiderivative when we have some letters in here. And again, we know that x is our variable because that's what's in our little f here. So the first term, we have a x to the b. So when we take the antiderivative, we're going to get a x to the b plus 1 divided by b plus 1 minus, now we have c over x. So the c will come out front, and we get c times the natural log of the absolute value of x, plus we have d to the x, that's exponential, so we get the same thing back, divided by the natural log of the base. And then finally we have cosine. The antiderivative of cosine is sine. So we have sine of gx, but that g is a number, so we have to remember to divide by g. So we're able to find basic antiderivatives even when we have these algebraic forms instead of numbers by applying the same rules. So as long as we're careful about them and we get really good at the formulas in that table, then we should be able to extend it even when it's not in the easiest form to try to figure out. So we talked about how antiderivatives are families of functions. So that means we can always throw on this plus c because we know that when we take the derivative, it'll disappear. However, sometimes we want a very specific antiderivative, something that answers some sort of question. And we're able to actually solve for c if we know any single point on the original function, on that antiderivative. If we have one data point, we can use that to solve for the specific c that would satisfy that data point, which means we'd plug in the x values into our antiderivative everywhere we see the x, and we'd set it equal to whatever the y value is, and that would mean we'd have all numbers plus c equals another number, and we'd be able to solve for c. So in the next example, we're going to look at how we deal with that situation when we have the initial data and how we're careful and go about solving for c. Example 6. Find the antiderivative and f of 0 equals 5. So that's the initial data we need to be able to solve for for a specific antiderivative that has a c specific to this data. So again, normally we're solving for a family of antiderivatives, but as soon as we have a point on that function, on the antiderivative function, we can solve for a specific one. So what does that process look like? So first we're going to find the antiderivative with the c in it, and then we're going to solve for c. So here my antiderivative will be x to the fourth over 4 plus 2x cubed over 3 minus x plus c. So here, first, I find my family of antiderivatives by using the rules from the table. But now I want to use the fact that f of 0 equals 5. So that means I'm going to plug in a 0 for all my x's, which is going to zero almost everything out. And I know that that has to equal 5. So that tells me that c has to equal 5, which means that my answer is going to be the same thing back, but with a 5 here for c. So we'll get rid of that. Get rid of that. I'll do plus 5. So my final answer looks like this, where I no longer have the plus c, and instead I have a specific antiderivative that satisfies that it's the antiderivative of the function and that f of 0 equals 5. Let's look at the next one. Part B. We have e to the 0.5x. So here, our antiderivative is going to be the same thing back, e to the 0.5x divided by the constant, which is 0.5 plus c. Now, if you divide by 0.5, that's the same thing as dividing by 1/2, which turns out to be the same thing as 2e to the 0.5x plus c. So that makes it a little bit easier to work with. Now, I also know that f of 0 equals 5. So if I plug in a 0 here, I get 2e to the 0 plus c equals 5. E to the 0 is going to equal 1. Anything to the 0 power will be 1. So 2 times 1 is 2. So if we have 2 plus c equals 5, that tells me in this case, my c has to be equal to 3. So my final answer here is going to be 2e to the 0.5x plus 3. Because that is an antiderivative that satisfies the definition. So when I take the derivative, I get e to the 0.5x back. But it also satisfies that f of 0, that the antiderivative at 0, has to equal 5. So I found my specific antiderivative for this case. Part C. We have 8 sine of 2x. So the antiderivative of sine is going to be negative cosine. So that means we're going to have 8 times negative cosine of 2x. Because there's a constant in there, we have to divide by 2. Let's simplify this a little bit. 8 divided by 2 will give me 4. So I have negative 4 cosine of 2x plus c. That's my sort of generic family of antiderivatives. But now I want to solve for c, right? So f of 0 equals 5. So if I plug in a 0, a cosine of 0 plus c equals 5. So cosine of 0 equals 1. So I have negative 4 plus c equals 5. That tells me that c equals 9 when I solve for that algebraically, which means that my antiderivative is going to be negative 4 cosine of 2x plus 9, because my c in this case is going to be 9. So again, if you don't have any data on the antiderivative family, then you just leave your plus c. However, if you have a point on the function of the antiderivative, you need to use that to solve for the specific c for that scenario. Let's look at one more example where we can look at this in application and think about some of the things that we might have to determine when we're thinking about antiderivatives in a context of physics. Example 7. Suppose a penny is dropped off of a building. When it hits the ground, the penny is traveling at a rate of 120 feet per second, where time is given in seconds. Part A. Find an equation for velocity of the penny at time t. Hint: acceleration due to gravity is a of t equals negative 32.2 feet per second squared. So that means if something is falling just naturally, it hasn't been launched or anything, it's just been dropped, that the acceleration due to gravity is negative 32.2 feet. So if we want to talk about velocity, we need to remember that acceleration is the derivative of velocity. So if we want to go the other way and go from acceleration back to velocity, we're going to need to find the antiderivative. So here, if we take the antiderivative of the acceleration, that will give us the velocity. We know that the acceleration is negative 32.2 dt. And so if our acceleration is constant, it will pick up the variable of integration. So that means we're going to get negative 32.2 t plus c. So our velocity is negative 32.2 t plus c. So we need to think about really carefully whether or not c is going to have a value here that has any meaning. So remember, at time equals 0, that's when you're holding the penny and you're about to let it go. So the velocity at time equals 0 is going to be 0 because that's the moment you let it go. It hasn't had time to pick up any speed. So if the velocity has to be 0 when t equals 0, that means that c would have to be 0 in that case as well. So my velocity function in this scenario is negative 32.2 t. B says, using your equation from part A, determine how long it will take for the penny to reach the ground. So we need to think about what we know and what we can put together here. So we know that when we drop the penny, the velocity is 0. But we also know that when it hits the ground, it's traveling at 120 feet per second. So if we set our velocity equal to 120 feet per second, then we can solve for the time when it reaches that velocity, and that will be the time when it hits the ground. So we're going to take 120 feet per second equals negative 32.2 t, and we're going to solve for time. Now, we have to be a little bit careful about our signs here, because notice right now that 120 is the opposite sign of 32.2, right? And so it doesn't make sense for these to be different signs. So the negative in this scenario indicates that the velocity, that this object is traveling in the downward direction, which means that we also want our rate of 120 feet per second to also be negative, because the penny was still traveling downward when it hit the ground. So when I solve for t here, I'm going to divide both sides by 32.2. I'm going to get approximately, because I'm rounding, 3.7267 seconds. So again, I'm traveling at this rate, headed downward, and I know that when I reach 120, I've hit the ground. So therefore, the time it takes me to hit the ground from when I've been dropped is 3.7267 seconds. Part C. Find an equation for the position of the penny at time t. What do we know about this equation when time is equal to 0? So remember, velocity is the derivative of position. So if we want to go backwards from velocity to position, we need to find the antiderivative. So again, we go back to our velocity equation, negative 32.2 t dt, and we find the antiderivative. So here that's going to be negative 32.2 t squared over 2 plus c. So here we can simplify this a little bit if we want to. So 32.2 divided by 2. We'll put this all over here. We'll call position s of t because that's generally the convention for position. But half of negative 32.2 is going to give me negative 16.1 t squared plus c. So that's my position equation. And then the other part of this question is, what do we know about this equation when time is equal to 0? So when time is equal to 0, the position should be the height of the building, right? Because that's how high the penny is in terms of position. So when t equals 0, then my function equals c, which means that c here, my plus c, is going to represent the height of the building. So, as you can imagine, part D wants to know, use your answer from parts B and C to determine how tall the building is. So how do we put this together? So remember, in part B, we determined that it took 3.7267 seconds to fall from the top of the building all the way to the bottom of the building, which means that if we were to plug that 3.7267 seconds into my position function, that the position after that time will have to equal 0 because that's the point where I hit the ground. So I'm going to take my time and I'm going to plug it into my position function. And when I do that, I'm going to get, so when I plug it in for t, I get negative 223.6 plus c. So that tells me, again, how tall the building is going to be, because I know the position at this time should be 0, because at time 3.7267 is when I hit the ground. So if that has to equal 0, that tells me that c has to equal 223.6. The position is going to be in feet, because remember, velocity was in feet per second. And so now I know how tall the building is. So I was able to use antiderivatives to find out a lot of interesting information about position and velocity and height because I had these methods to find the antiderivative.